Until now, we have been studying mostly quantum theories and physical phenomena which were discovered a relatively long time ago. So I think maybe the latest theoretical development we talked about, the path integral itself, goes back to the 1940s. Today in this video, towards the end of the video, I'm gonna tell you about a more recent theoretical development, so-called theory of quantum localization, or more precisely weak localization. And I will do so using the main ideas of the Feynman path integral. So I should mention that the full theory of quantum localization is an extremely complicated mathematical theory, and it could be a subject of a separate course, so I don't have time for that, and obviously we don't have the mathematical sort of background to talk about it. But it turns out that some basic ideas behind this phenomenon can be understood using the basic concepts behind the Feynman path integral, which comes handy here. So just in a few words, what I'm going to be talking about here is the following. So we know that in solid state physics, materials sort of can be divided into roughly two categories, insulators and metals. There are also semiconductors, but from this perspective, they're much like insulators. So, and what insulators are, if you apply a weak electric field, the electrons which exist inside the material don't move, and so there is no current really in response to such a field. So if you think about a piece of wood or something like that, so we obviously understand it's an insulator. It's not going to be a very useful electric component. On the other hand, if we have a metallic system, let's say a piece of copper, and if we apply electric field or voltage, there will be current in response to this electric field. And so this characterizes a metal. So in any real material, whether it's an insulator or metal, there are some imperfections, disorder, impurities, dislocations, all kinds of things. And this in metals, these impurities and dislocations, etc., so these imperfections, they lead to a finite resistance. Okay, and so first in the next slide, I will tell you about how this resistance comes about. But later on, we will see how the essentially classical theory of transport that applies to most metals at high temperature get modified as you go to lower temperature. And at low temperatures, quantum effects come into play. The wave nature of electrons come into play. And this is very interesting, and it turns out that under certain circumstances, you can get completely different behavior at low temperatures. The metals actually would become insulators. And this process of trapping electrons due to quantum mechanical effects is called localization. So of course, it's a very mathematical theory, as I told you, but we will try to get some idea about where it comes from. But before discussing complicated quantum theory, let me first talk about basic classical, very simple theory of how we can understand electrical transport in a metal. So here, this black dot labels an electron which can move around in a piece of metal. And these red dots here, larger dots, they represent some impurities of which the electron can scatter. And that's exactly what it does as it moves around. So it gets scattered by these red impurities. And so the trajectory of this electron is this diffusive trajectory, sort of random walk. Of course, it's not just one, there are many electrons in the metal, and they all experience this random walk, which in the absence of an electric field just averages out to zero. There is no net current, there is no preferential direction, there is nothing which breaks the symmetry. But now if we, let's say, apply electric field in this direction, the electrons which have a negative charge are going to move in the opposite direction preferentially. They're still going to move around in all directions, but there will be sort of a drift in one particular direction, and this will give rise to current. Now, it turns out that the first theory of this conductivity of this current in a metal was put together back in 1900. And this theory is a so-called Drude theory, which is a very simplistic theory that I'm going to explain now. So basically, the Drude model assumed that we can just view the electron as a classical particle, which therefore satisfies the classical equations of motion, the Newton equation, and in the presence of electric field, so the charge, let's say if the charge is Q, so it experiences this force due to the electric field, and these impurities, all these imperfections, he just replaced with the friction force. And this friction force was assumed to be proportional to the velocity. Let's say it sort of makes sense if you have a viscous fluid, for instance, and if you put an object and it's going to move in this fluid, so it's going to experience some force, friction, which is proportional to the velocity, and with a minus sign, of course, and there is some coefficient. So velocity is momentum divided by the mass, so we can write, instead of writing the friction force this way, we can write it as minus p over t of some tau, which is a time scale which describes momentum relaxation in this process. So in some sense, you may think about this tau as the typical time between collisions for the electron. But in the Drude model, it was just a sort of phenomenological parameter that described friction or momentum relaxation of this electron. And now what he did, he simply wrote down this model. And of course, we can write the left-hand side of the Newton equation as dp dt. And so the right-hand side, just putting this together, is going to be the electric force and this friction force. And in equilibrium, we demand that there is no acceleration of electrons. So if we if we take, let's say, a piece of metal, apply some electric field, eventually it's going to come to some sort of steady equilibrium. There is going to be a current, but there's not going to be indefinite acceleration of electrons. They're going to come to a certain sort of steady state, and this steady state will determine the current. Now, and from here, what we can do, we can just solve for the velocity. So momentum is equal from this equation is going to be equal q times e times tau, and velocity therefore is going to be just momentum divided by the mass. And at this stage, what we can do, so we can write the current. So the current is simply the charge of the carriers, in this case electrons, times the density of these carriers, how many of those participate in transport, and v is the velocity, which we just determined. And so if we put everything together, we're going to get this expression. So it's going to be this coefficient, which is called conductivity, and times the electric field. So by definition, actually, the conductivity is the coefficient of proportionality between the current and the electric field. And so this expression, this nq squared tau over m, is the so-called Drude conductivity, which, as you can see, is a purely classical entity. So there is no quantum mechanics here whatsoever. Now, embarrassing thing that I have to admit at this stage is that almost all sort of useful theories of metals, of transport in metals, rely on this Drude equation up to this day. So since for more than 100 years we've been using this equation, and in most cases it actually works fine. But fortunately, well, for us scientists, otherwise it would have been really boring. So if you go to lower temperatures, the situation becomes a little more tricky. And this is because quantum mechanics becomes important. So quantum mechanics come into play. And what it means is that in this picture, for instance, with how we can envision the appearance of quantum effects is that instead of just straight trajectories of classical particles, we're going to have waves bouncing around of these impurities. And so these waves are going to interfere with each other in some sense. So it's going to be the particle is going to interfere with itself, and these quantum interference effects are going to modify this picture very significantly. So now let us look at the electron motion in a metal, in a disordered metal, from a slightly different perspective. Actually, from a completely different perspective, because now we want to explicitly to turn on quantum mechanics, and we will use quantum mechanics, interpretation of quantum mechanics due to Feynman, and ask the question of what is the probability of for an electron to diffuse from an initial point to a final point F through this forest of impurities. And according to the Feynman, this probability can be written as the absolute value squared of a sum of quantum mechanical amplitudes associated with all possible classical paths, this diffusive trajectory. And here I'm just showing two such possible trajectories, this blue one and the black one, and these guys are going to interfere with one another. And this interference, so for instance, if I call this trajectory trajectory 1, and this is going to be trajectory 2, so the interference term which is going to appear due to this from this expression is going to involve a product of this black exponential e to the power I s1 h bar times the blue exponential, which is complex conjugate I s2 divided by h bar plus its complex conjugate. So all in all, the interference term coming from these two particular trajectories, again, this is just two examples. There are infinitely many such trajectories and infinitely many such terms. But in any case, each of these terms is going to produce this sort of cosine of S1 minus S2 divided by h bar. So this is basically the quantum interference terms. And the terms which don't involve the cross product of different trajectories are classical terms. So in some sense, these are the terms which are responsible for the Drude conductivity, the classical Drude conductivity that we obtained in the previous discussion. Okay, and so now the question of what is quantum mechanics doing, what are the quantum corrections, boils down to figuring out what these terms are actually. Now, in the beginning of this video, I mentioned something about temperature. I said, well, at high temperature, so these terms don't really matter. At low temperatures, they start to matter. And the reason this is the case is because at high temperatures, what temperature really is, it involves a lot of motion which occurs around these electrons, which are sort of doing their thing, moving around, diffusing around. But there is also, let's say, lattice vibrations, all kinds of things. This sort of shaking of the electron disturbs the phases. So in some sense, this is what is called sometimes in quantum mechanical literature, this is called dephasing. So basically here in this expression, whatever theory we're going to be doing, we're going to determine these actions, we're going to assume that phase, quantum mechanical phase, is going to remain constant during, or unperturbed, better to say, during the motion of electron along these trajectories. But it turns out that even if we assume that there is no disturbance of the phases and no dephasing, so classical physics in some sense protects itself in that these quantum interference terms tend to cancel each other out and completely disappear from the picture, and we'll actually have to search really hard in order to find the situation where they start being essential. And in order to see all this, let me estimate the typical action that appears in this equation. So remember that, well, at this stage we're just talking about particles bouncing around from these impurities, but otherwise, in between each scattering, they are free particles. So their energy is essentially just mv squared over 2, the kinetic energy of a free particle. And therefore, in order to estimate the action, we can just say that, by the order of estimate, so it's going to be mv, which is momentum, times another velocity, times dt, which is sort of, so this is going to be the total length of the trajectory, and this is going to be the typical momentum. So we can estimate our action on each path as the typical momentum of an electron times the typical length of the trajectory. So now, using this estimate, we can also estimate the typical quantum interference terms, which are described by the sum of over all pairs of non-equivalent different trajectories, L1 and L2. And now, instead of the action S, we write explicitly the typical momentum, which, by the way, is called Fermi momentum divided by h bar times the difference in length between the two trajectories under consideration. Or we can write it equivalently as the cosine, sum over all L1 not equal to L2, cosine of typical momentum times delta L divided by h bar. So it turns out that this argument of the cosine in the typical metal is actually very large. And this is because the typical velocity of electron in a metal is less than 1% of the speed of light, which 1/100th of the speed of light, which still is pretty fast. And therefore the typical Fermi, the typical wavelength turns out to be less than a nanometer, 10 to the -9 meters, which is usually much smaller than the distance between these red dots here. So I'm just giving you facts. It's not by any means obvious. It doesn't follow from the previous discussion. I'm just giving you certain information. And the bottom line here is that the typical wavelength, in some sense, you may think about electrons really being a wave. And this wavelength is much, much smaller than the distance between these red guys. And so the interference terms are not very important. And how it plays out here is that, so this typical ratio of delta L divided by essentially this lambda is very large, and so you have different trajectories contributing to this sum, and so you have cosines of different phases, completely random phases. And cosine, as we know, is the function which can be positive or it can be negative, depending. So if this is our cosine of phi, and this is phi, so it can be positive or negative. And so if we completely pick this phase is completely random, so the average value of the cosine is going to be 0. So the terms with different signs of cosine basically cancel each other out, and this is exactly what happens with quantum interference terms. And so seemingly classical physics survives, and we can just completely forget about this quantum interference phenomenon. So fortunately, it's not quite the case. It's almost the case, actually, in not very disordered metals in 3 dimensions, but it's not always the case. And how the quantum interference terms sort of appear, we can see by noticing that there is a very special class of trajectories, where this randomization and this cancellation doesn't happen. And these are so-called self-crossing trajectories, which actually one of those trajectories is sort of presented here. So this, you see there is a loop here when an electron can actually travel in the clockwise direction, and this is going to be our path number 1, or it can decide to travel in the opposite direction, counterclockwise direction, in which case it's going to be a path number 2. And the two paths are going to have, they're going to be different paths, but they're going to have exactly the same length. And therefore, the quantum interference terms corresponding to these paths are going to survive. This phase difference is going to be 0, and these terms are going to play out very significantly. And so this is what we're going to discuss in the second part of this video. Now, going back a little bit to physics, in order just to give you an intuition about what it has to do with conductivity. So we can sort of can intuitively understand that the easier it is for an electron to move from an initial point to some distant final point, the better this material conducts. Okay, the better it diffuses, the better it conducts. And at the classical level, it is just determined by this Drude conductivity. On the other hand, the easier for the electron to return to the same point, the more often it is sort of goes back and back, so the worse conductor it is. So in some sense, the probability to have these self-crossing trajectories should, in general, by general arguments, reduce the conductivity, and this is exactly what happens in most cases, and therefore it is called so-called weak localization. Basically, it tries to bring electron back to where it came from.